So, very good morning. So, today we are moving into the last lap of the topic on fluid properties. This is module 8. So, in this module is fully devoted to numerical problems. The first phase on problems involving surface tension and capillarity, and the second phase in which numerical problems which have been random picked from the web. The questions that have been asked in competitive examinations like GATE or Indian Engineering Service, some sample problems have been discussed. So, let us move into the numerical problems one by one. So, the example number is given in continuation of the numerical problems that we have solved before in the previous modules. Calculate the capillary rise in a glass tube of 3 millimeter diameter when immersed in water at 20 degrees Celsius. So, take surface tension for water at 20 degrees centigrade as 0.0736 Newton per meter. What will be the percentage increase in the capillary rise if the diameter of the glass tube is 2 millimeters? So, before we proceed with the solution of this numerical problem, so let us summarize what we discussed on surface tension and capillarity in the previous module, that is module 7. So, surface tension and capillarity are properties exhibited by liquids, only liquids. So, surface tension, that is the liquids, the liquid molecules have cohesion as well as adhesion. Cohesion is the intermolecular attraction between molecules of the liquid itself, whereas adhesion is the affinity shown by the liquid molecules towards the solid surface with which it comes in contact. So, some liquids will wet the solid surface more, that means the affinity is more, the adhesion is more. So, when adhesion is more than cohesion, when adhesion is predominant or dominant over cohesion, then there will be capillary rise, and when cohesion is dominant than adhesion, as in case of mercury, it will be capillary depression, capillary fall, when you are dipping a capillary tube inside a container containing mercury. So, now, water, this is water coming in contact with the glass tube, this is the case of. So, in the first case, the diameter of the glass tube is 3 millimeters. So, let us put it in meters, that is 3 multiplied by 10 power minus 3 meters. Then the surface tension of water depends upon the fluid that is in contact with the particular liquid, and also the temperature. So, surface tension of any liquid must be quoted at the temperature as well as what is the fluid in contact with the particular liquid. Now, water is in contact with air now here. So, 20 degrees Celsius is the temperature, it is given as 0.0736 Newton per meter is the surface tension. So, you are asked to find out the percentage increase in capillary rise when the diameter of the glass tube is 2 millimeters. Now, this expression we derived, that is the capillary rise is given by 2 sigma cos theta by gamma r. So, sigma is the surface tension of water in contact with air in this case, theta is the angle of contact. So, for water in contact with the glass, we discussed yesterday, theta is 0, that is it is concave downward, and this theta is 0, the angle of contact is 0. So what is cos 0? Cos 0 is 1. Cos 0 is 1. Sigma is given. So radius, the diameter is given. So R will be d by 2. This is diameter divided by 2. And gamma is the specific weight of water, that is 9810 Newton per meter cube. So 2 sigma is 0.0736 Newton per meter. It is the force per unit length of the liquid film to keep the liquid film in equilibrium, that is surface tension. Then cos 0, theta is the angle of contact, which is 0 degrees in this case. Gamma, specific weight of water, and radius for 3 millimeter diameter of glass tube, it is 1.5 multiplied by 10 power minus 3 meter. We get the capillary rise as 0.01 meter. Now, you are asked to find out the percentage increase in the capillary rise if the diameter of the glass tube is 2 millimeters. See, now the capillary rise is inversely proportional to the radius. So, as the radius or the diameter of the glass tube decreases, the capillary rise will increase. So, from 3 millimeters, the diameter now becomes 2 millimeters. So, let us find out the capillary rise of water when diameter of the glass tube is 2 millimeters. So, let that be H2. So, 2 sigma cos theta by gamma R. So, here only the change is in the radius, that is 1 multiplied by 10 power minus 3 meter, it becomes 0.015 meter. So, H1 is, that is for 3 millimeter diameter glass tube, it is 0.01 meter. For 2 millimeter diameter glass tube, the capillary rise is 0.015 meter. So, what is the percentage increase? It is H2 minus H1 divided by H1 multiplied by 100 is the percentage increase. So, H2 is 0.015 meter, this is 0.01 meter. So, you get 50% is the increase in capillary rise when the diameter of the glass tube is reduced from 3 millimeters to 2 millimeters. Okay. We take the next problem. Show that for two vertical parallel plates, say you consider flat plates which are thin, the thickness is thin, and they are kept t distance apart. The distance between these two parallel plates, which are that is t, they are held partially immersed in a liquid of surface tension sigma and specific weight gamma. You have to show that the capillary rise is given by H is equal to 2 sigma cos theta by gamma t, where theta is the angle of contact. Now, the distance between these two parallel plates t is such that it is acting like a capillary tube, and you can consider the equilibrium of the two vertical parallel plates separated by a distance t, held partially immersed in liquid or specific weight gamma. Now, what happens? The liquid level rises. There is a capillary rise because of the small distance t between the two parallel plates. Now, for the equilibrium of vertical forces acting on the mass of liquid, that is you have to consider the equilibrium of the mass of liquid above this portion of liquid above the general surface of liquid. This is the general surface of liquid in the container. So, you have to consider the equilibrium of this mass of liquid. There is a hatched portion, red hatched portion. So, consider the weight of the liquid of column H that must be balanced by the force at the surface of the liquid due to surface tension. So, considering unit length of the liquid film, that is perpendicular to the plane of the paper, because it is a parallel plate, it is not a tube. So, let us consider unit length of the liquid film perpendicular to the plane of the paper, that is in this direction, perpendicular to the plane of the paper. And then you can equate the two forces, that is weight of liquid column H. Then you consider 1 meter perpendicular to the plane of the paper, that is balanced by the force due to surface tension. Now, let us find out the weight of the liquid column. which is nothing but specific weight multiplied by volume of liquid column. Volume of liquid column H. So how will you find out the volume of liquid column? That is distance between the two vertical parallel plates multiplied by height of liquid column multiplied by unit length perpendicular to the plane of the paper will give you the volume. So T is the thickness of the column, vertical column, and H is the height of the vertical column, and the length of the column between the two parallel plates you are considering is 1 meter perpendicular to the plane of the paper. So T multiplied by H multiplied by 1 meter. So T multiplied by 1 by H. So multiply by specific weight. So specific weight is Newton per meter cube. Volume is in meter cube. So you get the force. So this is the weight of the liquid column. Then force due to surface tension, that is vertical upward component of surface tension, that is sigma cos theta. Sigma cos theta is the angle of contact is theta. So sigma cos theta is the vertical component of sigma multiplied by length of the film on which the surface tension acts. So what is the length of the film? So it will be a rectangle. So you are considering 1 meter length perpendicular to the plane of the paper, that is this much, and this distance is T, is also T. So we have to, this is the perimeter, that is the perimeter of the liquid film on the top at the meniscus on which the surface tension acts. So it is 1 meter plus 1 meter plus T plus T. So you get 2 meters, 2 meters plus 2T, 2 meters plus 2T, that is 2T plus 2. Okay. So sigma cos theta multiplied by 2T plus 2. So equate these two and then find out H. We can prove that H is equal to sigma cos theta by gamma T. So next problem. Calculate the maximum capillary rise of water at 20 degrees Celsius to be expected between two vertical clean glass plates spaced 1 millimeter apart. Take sigma. So just now we have derived the equation. We can use this equation where T is the distance between the two vertical parallel plates, that is 1 millimeter, expressed in meters, that is 10 power minus 3 meter. It is water in contact with glass tubes, therefore the angle of contact is 0. So cos 0 is 1. Sigma, that is given 0.07358 Newton per meter. So we will get the capillary rise like this. Next one, a capillary tube having inside diameter 5 millimeters is dipped in water at 20 degrees Celsius. Determine the height of water which will rise in the tube. Take sigma equal to 0.07358 Newton per meter and angle of contact theta equal to 60 degrees. Specific weight of water is given. So this is a straightforward problem. You can solve. So specific weight, this value has to be taken, 9790 Newton per meter cube given. Angle of contact is 60 degrees. Angle of contact is 60 degrees. Here it is not 0 because it is not in contact with maybe glass. So it is 60 degrees. So put theta equal to 60 degrees. Surface tension is given. Specific weight is given. And radius, so 5 millimeters divided by 2.5 millimeters, so that will be expressed in meters. So you get 0.003 meter or 3 millimeters. By how much this is a problem on surface tension. By how much does the pressure in a cylindrical jet of water 4 millimeter in diameter exceed the pressure of the surrounding atmosphere if surface tension of water is 0.07358 Newton per meter. For cylindrical jet, for liquid jet, which is cylindrical in cross section, we have already derived this formula. The pressure inside the jet in excess of the outside pressure, that is atmospheric pressure, is given as P is equal to sigma by R, where sigma is the surface tension of, here it is water jet in contact with the air, that is 0.07358 Newton per meter, and the diameter is 4 millimeters. So, the radius will be 4 by 2, express it in meters, multiply by 10 power minus 3, and then you will be getting the pressure as so much, 36.75 Newton per meter square. Then again, this is a problem on capillary rise and capillary depression. Capillary rise in case of water and capillary depression in case of mercury. You have the glass tube of 4 millimeters. So, you are asked to calculate the capillary effect when the glass tube is immersed first in water and then in mercury, both liquids at the same temperature 20 degrees Celsius. Then the values of surface tension of water and mercury at 20 degrees Celsius in contact with the air are respectively given. Angle of contact for water is 0, angle of contact for mercury with glass is 130 degrees. So, find out the first capillary rise of water in glass tube, then that comes to 7.5 millimeters using the formula for capillary rise, and then capillary depression, the same formula using the data for mercury. The specific weight of mercury is 13.6 multiplied by 9810, that is specific weight of the standard fluid, that is water, you get 133416 Newton per meter cube. Then specific, the surface tension of mercury in contact with air at 20 degrees Celsius is given in the problem statement. Then angle of contact of mercury with glass, that is it is convex upward, right, and this is the direction of sigma, and this angle is 130 degrees. 30 degrees. So, capillary depression is found to be 2.49 millimeters. So, this is another problem on capillarity. So, you have a U tube, the inside diameters of the two arms, say this is the left arm and this is the right arm. The left arm has got a diameter of 1.5 millimeters, the right arm has got a diameter of 1 millimeter. Now, the U tube is partially filled with water having surface tension of 0.0736 Newton per meter and 0 contact angle. What will be the difference in the level of menisci between the two arms as shown in figure below? So, it is partially filled with water. So, there is a the diameter of the left arm of U tube, that is D left, is 1.5 millimeter, diameter of right arm of U tube D right is 1 millimeter, surface tension of water in contact with the air is given, then contact angle for air water glass interface is 0 degrees, then radius is nothing but you divide the diameter by 2, so for left and then for right arm. Then capillary rise H in a tube of radius r is given by the usual formula for capillarity, 2 sigma cos theta by gamma r. So, capillary rise in tube of radius r, that is here the radius is 0.75 millimeter, here the radius is 0.5 millimeter. So, for 0.75 millimeter, that is 0.75 multiplied by 10 power minus 3 meter, you get 20 millimeters is the capillary rise. Then capillary rise in tube of radius r will be, you get 30 millimeters. So, here this is 30 millimeters and here it is 20 millimeters. So therefore, in the U tube there will be a net capillary rise in the right limb of radius 0.5 millimeter. The net capillary rise is given by H2 minus H1, that is 30 millimeters by 20 millimeters, that is 10 millimeters. This is the required result, 10 millimeters. So here it is 30 millimeters, I am sorry, here it is you get 30 millimeters, here you get 20 millimeters, say from some reference like this, and the difference is 30 minus 20, 10 millimeters. Okay. Is another problem. Air is forced through a tube of internal diameter of 1.5 millimeters, immersed at a depth of 1.5 centimeters in a mineral oil having specific gravity 0.85. Calculate the unit surface energy of oil if the maximum bubble pressure is 150 Newton per meter square. See, I have a chamber in which I have a mineral oil of specific gravity 0.85 and air is forced through a pipe, right, into the chamber having mineral oil. The internal diameter of the tube is 1.5 millimeters. That is the effective opening of the effective diameter through which air is forced is 1.5 millimeters, and the tip of the tube is immersed at a depth of 1.5 centimeter below the free surface or whatever it is. Calculate the unit surface energy of the oil if the maximum bubble pressure is 150 Newton per meter square. I'm sorry. So let us put the data in with the proper notations. The diameter of the tube, small d is 1.5 millimeters, put it in meters, 0.0015 meter. Radius, half of that, r, that is 0.00075 meter. Depth of immersion, that is, I put it as h, that is 1.5 centimeter, this is h. 1.5 centimeters, that is 0.015 meter. Specific gravity of oil is given 0.85. Specific weight of oil will be specific gravity multiplied by specific weight of water, that is a standard liquid 9810. So you get 8338.5 Newton per meter cube. Maximum bubble pressure is 150 Newton per meter square. You are asked to find out the unit surface energy of the oil. Now pressure at the top of tube where the bubbles are released into the mineral oil due to the depth of oil of 1.5 centimeter will be specific weight of oil multiplied by h, that is 125.1 Newton per meter square. So the pressure that is prevailing at the top of the tube here will be pressure increases with depth. So we will see about pressure when in the next topic, that is fluid pressure and measurement. So now for the time being you take this expression. So it is gamma is specific weight of oil, h is the depth of the tip of the tube at which air is blown into the immersed oil. So h is the depth of the tip from the surface of oil. So you get the pressure here as 125.1 Newton per meter square. This pressure acts vertically downward on the top of the tube. So the pressure will always act vertically, that is normal to the tip of the tube. So pressure of air bubbles released to the top of the tube. So what is the pressure of air that is released to the top of the tube? That is 150 Newton per meter square. So as the bubbles are released up through the top of the tube, this pressure acts vertically upward. Okay, this is acting upward because air is released in the upward direction. So P bubble acts in the upward direction, and this P, that is this one, this acts in the vertical downward direction. This acts in the upward direction. So what is the effective pressure? The effective pressure due to surface tension in each air bubble is given by P is equal to P bubble, which is higher, 150 Newton per meter square, minus the pressure at the tip of the tube due to 1.5 centimeter depth of oil from the surface of oil, that is 125.1 Newton per meter square. So this comes to 24.9 Newton per meter square. So we have P is equal to is a bubble. It's a bubble means it's something like a soap bubble. We have seen the effect of surface tension on a soap bubble. So the bubble, it has got air inside as well as air outside in that form. So P is equal to 4 sigma by R is the relation you should use. So you go back to module 7 and find out this derivation that we have made, the illustration of surface tension on a soap bubble, and we have derived the pressure inside the bubble in excess of the outside pressure P is given by 4 sigma by R. So 24.9 Newton per meter square is the effective pressure due to surface tension in each air bubble, and sigma is the surface tension of acting on the bubble in contact with say the liquid or oil divided by R. So you get the value of surface tension, sigma. So this is another problem. Name the characteristic fluid properties to which the following phenomena are attributable: rise of sap in a tree, spherical shape of a drop of liquid, cavitation, flow of jet of oil in an unbroken stream, water hammer. So rise of sap in a tree is due to capillarity, the attributable property for rise of sap. So the sap rises in the upward direction, right, through the tree, that is due to capillarity. Spherical shape of a drop of liquid, that is we have seen the liquid droplet getting separated from the main body of liquid, it attains the spherical shape which has got the minimum surface area, that is due to surface tension. Then cavitation, it is due to vapor pressure. We will study about cavitation in the hydraulic machinery. Then flow of jet of oil in an unbroken stream, that is because of the property viscosity. Then water hammer, which I mentioned in compressibility. So water hammer is a phenomenon that occurs due to sudden closure or of valve, right, in flow through pipes, that is due to compressibility. Therein we will talk about the elasticity of the liquid that is flowing through the pipe, wherein we talk about the compressibility of liquids. Normally the liquids in engineering, in most of the engineering problems, are considered incompressible, but here in this case we consider the elasticity of the liquid that is flowing through the pipe or the compressibility. So water hammer is a phenomenon related with compressibility of the fluid. This is another problem on surface tension. Air is introduced through a nozzle into a tank containing water to form a stream of air bubbles. The bubbles have a diameter of 2 millimeters. Calculate by how much the pressure of air at the nozzle must exceed that of surrounding water. Assume that the surface tension of water in contact with the air is 72.7 into 10 raised power minus 3 Newton per meter. So I think this can be worked out, right? So here you have P is equal to 2 sigma by R, and we can find out what is the pressure of air at the nozzle. Calculate by how much the pressure of air at the nozzle must exceed that of the surrounding water, that is P. Okay, now let us go through some of the problems which have been random picked from the web on the the questions that have been asked in the competitive examinations such as GATE or Indian Engineering Services pertaining to civil engineering. So this is the problem number, the question number, which appeared in GATE examinations 2022 in civil engineering in set 2. The dimension of dynamic viscosity is, so dimension of dynamic viscosity we discussed when we discussed about viscosity. Now We know that the mass unit of dynamic viscosity is kilogram mass per meter per second. Kilogram mass per meter second. So dimension of kilogram is mass, dimension of meter is length L, dimension of second is T. So what about dimension of dynamic viscosity? So it is m L power minus 1 T power minus 1. So this is the correct answer. This is the correct answer. Okay, option D. This is again another MCQ asked in GATE 2021 examinations, civil engineering 4 known. It's question number 3. Kinematic viscosity is dimensionally expressed as, kinematic viscosity, the unit is meter square per second. Kinematic viscosity nu, the SI units is meter square per second. Okay. The dimension of meter is L, the dimension of second is T. So meter square means it is L square by T. L square by T. So this is the correct option. The correct option is option B. Now this is Indian Engineering Services Examinations 2022, Civil Engineering Preliminary Examinations. Preliminary Examinations MCQ. Question number 110 in that. What is the viscosity of a liquid whose kinematic viscosity is 6 Stokes and specific gravity is 1.90? So kinematic viscosity is given, that is 6 Stokes. 6 Stokes, 1 Stoke is what? 1 Stoke is 1 centimeter square per second. So 6 centimeter square per second. So centimeter square must be converted into meter square. So 1 centimeter square is 10 power minus 4 meter square. So 6 centimeter square multiplied by 10 power minus 4 meter square per centimeter square. So you get 6 into 10 power minus 4 meter square per second. So this becomes 0.0006 meter square per second. Then specific gravity is given 1.9. So what about the viscosity of liquid? Mu, we know that nu is equal to mu by rho. Nu is the kinematic viscosity, mu is the dynamic viscosity, and rho is the mass density. So nu is known. Rho is what? The specific gravity of the liquid is given 1.9 multiplied by mass density of the standard liquid, that is water, that is 1000 kilogram per meter cube. You get 1900 kilogram per meter cube. So mu is equal to nu rho. Nu multiplied by rho. Nu we have just computed in SI units, 0.0006 meter square per second. Multiplied by 1900 kilogram per meter cube, you get 1.14 kilogram per meter second, or 1.14 Newton second per meter square. 1 Newton second per meter square is 1 poise. So 1.14 Newton second per meter square is 1.14 I think there is some mistake here. 1 poise is 0.1 Newton second per meter square. This is wrong. I'm sorry. 1 Newton second per meter square is 0.1. Sorry. 1 poise is 0.1 Newton second per meter square. Therefore, (1.14 Newton second per meter square will be 1.14 into 0.14 1.14 Newton second per meter square will be 1.14 into 0.1 divided by, I'm sorry, 1 poise is 0.1 Newton second per meter square. Therefore, 1.14 Newton second per meter square will be 1.14 into 1 divided by 0.1, that becomes 11.4 poise. So, there is a mistake, this is not correct, this is 11.4 poise. 11.4 poise. So, this is the correct option. So, please note this correction, this is wrong. The answer is option B. So, the error is here. So, I apologize for that. 1 poise is 0.1 Newton second per meter square. Therefore, 1.14 Newton second per meter square becomes 11.4 poise. So, the answer is option B is the correct. Option A is wrong, option B is the correct answer. Okay. Now, this is Indian Engineering Services Examination Main 2020 Civil Engineering Paper 2, and you have a compulsory part, that is question 1 subdivision B. In that one, it is a compulsory question for 6 marks. So, this is a numerical problem on viscosity. A rectangular plate 0.5 meter by 0.5 meter dimensions weighing 500 newtons slides down an inclined plane making 30 degrees angle with the horizontal at a velocity of 1.75 meters per second. If the 2 millimeter gap between the plate and inclined surface is filled with a lubricating oil, find its viscosity in poise. So, a similar sort of problem we discussed previously on viscosity. So, I request the viewers to go through that, and if you have gone through that solution and understood, you can very easily solve. This is of the same type. So, we have listed the data. The size of the plate is a square 0.5 meter by 0.5 meter. Weight of the plate is given. Angle of plate, inclination of the plane with the horizontal is given theta, that is 30 degrees. So, the velocity with which the plate slides down the inclined plane is given. The gap between the sliding plate and the inclined plane is given 2 millimeters. You are asked to find out the viscosity of the lubricant that is in the gap between the sliding plate and the inclined plane. So, we have to consider the equilibrium of the sliding plate. You take Newton's law of viscosity, tau is equal to mu multiplied by dV over dy. So, tau is the shear stress developed due to the shear force caused by viscosity of lubricant between the inclined plane and the sliding plate. The viscous force Fv, so tau is equal to viscous force due to viscosity, the shear force due to viscosity of fluid divided by area of the plate in contact with the inclined surface. So, area of plate is 0.5 by 0.5, 0.25 meter square. dV over dy is the velocity gradient. So, as the gap is very small, 2 millimeters, let us assume the velocity gradient to be linear. So, it becomes V over y. So, V is the velocity with which the plate slides down the inclined plane, and y is the gap, annular gap thickness. I am sorry, the not annular gap, the gap between the inclined plane and the plate. So, it becomes 875 per second. Then the force responsible for sliding of the plate down the inclined plane is the component of self weight of plate acting downward along the surface. So, we can use this right angle triangle and find out what is the component of the plate that is responsible, component of the weight of the plate that is responsible for the movement down the plane. So 250 newtons is the component, that is W sine theta. For equilibrium of the plate, the force due to sliding down the inclined plate must be equal to the shear force due to viscosity of the lubricant acting along the inclined plane. So PS acts in this direction and the viscosity acts in the opposite direction. That is the resistance to flow. So PS is equated to Fv, that is 250 newtons. So Fv by A is mu into V by Y. So from here you can get the value of mu, that is dynamic viscosity, which comes to 1.143 Newton second per meter square. This fundamental trigonometry, this we have already discussed in a similar sort of same type of problem in a previous module. So you can easily understand. So with this we come to the closure of module 8 and also the completion of fluid properties, and I request the viewers to glance through the things and let us meet in a different topic soon. Thank you very much.